Okay, good morning, everyone. I hope you enjoyed the barbecue yesterday and you had a nice evening. So we have our third day of last week of the program, and we start with Mairi Sakellariadou, and she will tell us about gravity in the era of gravitational wave astronomy. Please, the stage is yours.
Okay, so good morning and thanks for coming. Let me start by thanking the organizers, Alessia, Ben, Luca, and Stravan for the invitation to this program. It's always a pleasure to be in a program at Nordita, so thank you very much. And thank you as well for taking care of the barbecue yesterday. So I will talk about what you can do with gravitational waves regarding gravity. And as you can see, deliberately, I didn't put quantum in the title because there are some things that refer to quantum gravity. There are some issues which refer to modifications of gravity, which could have been inspired by a quantum gravity proposal or not. And of course, there are many things that one can do, but I will concentrate on what we are doing with gravitational waves and what we plan to do. So, why doesn't go to the next? Okay, so there are strong affinities between quantum gravity and cosmology. So, of course, one expects that the correct theory of quantum gravity, once we'll have it, it will be able to somehow cure some of the pathologies of classical theories that we have. The problem of initial singularity, to give some kind of solid explanation, not a phenomenological model of the very early and very late kind of accelerated expansion. The origin of density perturbations, to say something about the explanation of the space-time dimensionality, and as well the emergence of space-time and of the universe. On the other hand, cosmology is probably at least a very powerful, if not the only way, to test models of gravity. By that I mean the quantum theory of space-time geometry. And if you want to reproduce quantum gravity in the lab, then we will need extremely high energy scales, 10 to the 19 GeV, which I think in a rather foreseeable future is a dream. But as I wrote here, we live within a big experiment. We live within an experiment that keeps going for about 14 giga-years and releases information that cover about 42 billion light years of space, which is our universe. And therefore, the idea would be to use cosmology in order to test some of the theories of quantum gravity, of the proposals, since they are going to leave some kind of fingerprint in the universe. And what I'm going to concentrate today is about gravitational waves. For instance, it was mentioned yesterday during the talk of Francesca, when she talked something about a group field theory. Indeed, in that framework, we were able to show initial kind of expansion. We were able somehow to even give some kind of idea about the issue of cosmological constant. But today, I'm not going to talk about any of that. I'm going to say how we're going to use gravitational waves to test theories of gravity. So within the LIGO-Virgo-KAGRA collaboration, here you can see all the public events we have so far. Right now, we are in the 4th observing run that it was supposed to go until beginning of June 2025, but it may go much beyond that. And you can see that we have something like 100 public events, a bit more than that, and we expect a few hundreds by the end of the observing run that we're going right now. So since I'm not sure whether everyone in the audience is very familiar with what we are doing with gravitational waves, let me very briefly say a few things which are going to use as I go along. It's no problem. So depending on what is the gravitational wave signal that we have, and therefore what is the origin, which means what is the way that we try to detect it, we classify them in this way: transient, persistent, depending whether they remain very short in your interferometer or they stay much longer. Yesterday when I said transient, somebody asked the question, what do I mean by transient? The same way, They are phase incoherent and phase coherent. We don't know the source. Can we treat the phase deterministically or not? And depending in which part of this plot you are, they are different, the origin of these gravitational waves, and different the way that you try to detect them. So far, what we have seen goes to the upper corner, transient phase coherent, which they come from the merger of two compact objects. I will refer on that, and I will refer as well on the gravitational wave background. These are the two parts of the corner that we'll discuss later. And something else I would like to mention, because I will say a few things about the three phases that we have, the in spiral, the merging, and the rig down. This is the process. In spiral, large separation, low speed, weak gravitational field. Merger, short separation. The speed is close to the speed of light, and you have a strong gravitational field. And finally, you have the ring down. The way that you try to study these three distinct phases of the coalescence that you have, post-Newtonian methods for the in-spiral, numerical relativity for merger, and perturbation theory for the ring down. And I will refer to them as I will go along. So I would like just to state, the definitions so we're all at the same phase. So there are two types of tests which we do. I'm going to start with the model-independent test of GR. And at the end of the talk, I'm going to make summary. I will just give some examples of specific models, one referring to primordial black holes, one referring to Chern-Simons gravity. Just because they were mentioned yesterday, I would like to say what we do there, what are the constraints that we can put. So here what the idea is, we compare the predicting gravitational wave templates that we have, okay, with the data which we receive for our interferometers. And that means that we do a rather model agnostic test. And again, we have two different kind of test. Consistency test, which means how consistent is the signal that we have observed with what is the waveform that general relativity tells us. And then parameterized test that we're going to use a particular parameterization, which we expect that's going to catch up some of the effects that we go beyond a GR proposal. The consistency checks, which we do, you assume that GR is correct, and you try to compare your waveform with the data. And we have the residual test, which is the most generic test. You don't need any parameterization. What you try to do, you say, I'm going to see whether I have any deviation from the GR, and the spiral merger ring down test. That's why I introduced what I mean by that before. So what you do, you take your data. From there, you are going to subtract what GR tells you, and what you expect at the end of the day, if GR is correct, is to find the noise. So that's what is the first test. The in-spiral merge, which is the simplest one that you can do. The in-spiral merge ring down test, it tells you I'm going to find which are the parameters of my compact object. I'm talking again about transients. The parameters means the mass of the spin. If I consider only in spiral, or I consider as well the merger and the ring down. If GR is correct, then the two tests should be the same. The masses and spin should be the same. So by doing this test, so far, from the 100 events that we have, the transient effects, we found no deviation from general relativity. Okay, now the parameterized test. You do a model-independent test that is going to introduce some generic parameters which you expect are going to reveal some kind of signature of non-GR kind of influence. So you have the in-spiral test, which you want to verify the post-Newtonian structure, and the ring down test. So what you do in the first test, you take your waveform, you work in Fourier space, and you are going to write both the amplitude and the phase, here I type the phase, which depends on the frequency, as a sum of post-Newtonian order kind of terms, okay, which you are going to treat each of these post-Newtonian order alpha n as independent kind of variable, and then you are going again to make a comparison between the waveform that you have and the data, okay? Now, there is a challenge here. is that there are theories beyond GR where you cannot really write them in this way. The phase is not the most important. You cannot write in this spiral, this kind of post-Newtonian approach. And there is another difficulty there is how are you going to do the mapping at the end of the day with a particular theory? The second is the ring down test. And here, the attempt, which is very difficult to be done, there are some approaches here, but again, this is under investigation, to construct a parameterized ring down waveform, which is based on the perturbative treatment of the ring down that you have in the GI. The difficulties which you have here is that spin seems to be important, and it's quite difficult to model the spin dependence in beyond GR theories. And the second theory that you do not have here the Teokolsky equation where you can separate the modes. So it's rather difficult to be able to calculate the quasi-normal modes of the ring down in a beyond GR theory. And there is, again, investigation. It is an open question. Now, given that you have a modified theory of gravity, the difference that you could have within GR, they can be within the generation, the propagation, the polarization, and the remnant property. So I'm going to go through each of them, okay? So the generation, this is going to give a relation between the radiation that goes out from your transient and arrives to your detector. This is a difficult problem even within GR. Propagation. You have three effects here: dispersion, birefringence, and amplitude damping. So dispersion. Here, for instance, I take as an example Lorentz violating dispersion relation. So you have this extra term, which is a phenomenological term. This capital A and alpha depends on which theory with Lorentz violation you're going to include. And then I give some examples: double special relativity, extra dimensions, Horava-Lipschitz theory, theories with no commutative geometry, how this dispersion relation changes. Birefringence. Now there is, again, quite some models. Chen-Simons gravity, ghost-free scalar tensor theory, symmetrically parallel equivalence of GR, Horava-Lipschitz gravity. So you have that the gravitational waves, as they propagate, the amplitude of left and right modes is different. So there, what you're going to have is a parity violating effect. So this is the birefringence. We use all of them. I will come back to that later. Amplitude damping. Here, I write down in the evolution equation, okay? I am in conformal time, and then this nu and this mu here, and gamma, in the case of GR, they're equal to 0. Mu is the graviton mass, gamma is anisotropic stresses, and that's how this equation is going to change, and you have to solve it if you are in a theory beyond GR. So you have massive gravity, for instance, or propagation of gravitational waves different than the speed of light. Polarization. Yet in a theory beyond GR, you might have extra polarization modes. So you might have instead, apart from the plus cross, the vector and the breathing and longitudinal mode. So here I have my test particles, which are in the XY plane, and in the Z plane perpendicular for the plus cross and the breathing mode. And on the right direction for the other three is the propagation of gravitational waves. And I will tell you how we try to test and put constraints if we have theories with extra polarization modes. Now, that's the standard one, plus cross the standard GR. And you have two vector and two scalar one, depending on the theory. So in any modified theory of gravity or in any kind of quantum gravity inspired model beyond GR, you could have any of these kind of difference. And then the idea is to find out which one, if you can, and to do the mapping and put constraints in the theory. That's what I will try to highlight for some examples. Yeah. Here. If you have extra dimensions, you could have a new non-vanishing, okay? But that's a very general thing to say how it would, and what you are doing there, you are going to compare the luminosity distance from gravitational waves and from electromagnetic. And there is a constraint. So now, if you have additional fields or higher curvature corrections, then these are going to change the waveform because they're going to change the energy and the angular momentum. And what you do, if you do some test of the in-spiral part of the waveform in a post-Newtonian kind of framework. So the idea which you need to have in mind is this kind of plot that I put here. If you are in the horizontal axis, that means that gravity is extremely weak. If you are in the vertical axis, that means that you have almost static theory, okay? And any departure from that gives you the weak gravitation sources and slowly moving. So this is the relation which you have, and you expand that in a post-Newtonian order. So within the first three observing runs, what we did, we wrote down, when you see a tilde, that means I am in Fourier space, is a frequency dependence, this is the amplitude, this is the frequency, the phase, I'm sorry. And what we have done, we introduced parametric deviations to this in-spiral phasing in a post-Newtonian order, and this is the result that was found. So if you have a theory beyond GR, you might have this kind of dipolar radiation here is the -1 post-Newtonian order, and the results that we have here, okay, are in agreement as a function of the Cherenkov mass here, are in agreement with what we expect within the framework of general relativity, okay? Now, test of propagation, which is dispersion. So I give, for instance, an example here in the massive gravity. This is the extra term that you are going to have in the dispersion relation. This is the graviton speed. So what you are going to do, you are going to compare the time of arrival if you have an electromagnetic counterpart. So the general way that within the collaboration we write the kind of dispersion relation in a no-GR theory is by introducing this phenomenological term here. I do some mapping for different values. You can see for different values of alpha and capital A, you have a different kind of modified gravity field. What you would expect at that point is this extra term is going to give an extra contribution in the phase. Then we can calculate what is this extra correction in the phase. As the source is far away, this thing builds up as it arrives at your interferometer. And at the end of the day, with the data that we have, we were able to put constraint on these parameters, capital A and small alpha, depending if it's positive or negative. And then you can go back and you can do a kind of mapping with the theory that you have in mind and how you can constrain it. So that's the whole idea. And if we take the one data that we have with electromagnetic counterpart, then from the difference of the time of arrival of the signal, we're able to put constraints on the mass of the graviton, which is much better than the one that you get from the solar system. Yes, Robert. These are upper bound. So then a parity violation that I said before. Again, so here is a general way in an effective field theory approach that you can write, you can have a model that has parity violation. And then we're going to have these three parameters, C1, C2, which they depend on time. And this MPV is the scale at which parity violation appears. And then what you can do, if you have such a theory, that's how they are going to look like the left and right-hand side circular polarization modes. You can go and write the plus and cross modes, and you can see what will be the phase difference that you are going to have, which will depend on the parameters C1 and C2 and the Planck and the scale at which parity violation takes place. And then it was done. The most recent paper that I know is this one, 2021, which was a Bayesian inference kinds of study, and there were constraints in the upscale, in the energy scale at which parity violation takes place. So all what I'm saying here, you take this data, you go back to your favorite model, and you try to see how does it map with C1, C2, what are the constraints of the theory that you have. Yes, no, they are both of us, yeah. So the gravitational wave background that I said before, so the gravitational wave background is the equivalent of the electromagnetic background. So what we expect is that the universe is filled with gravitational waves, and we expect that some kind of deviations that we might have in the distribution of these gravitational waves at the end of the day can give us a map of the sky, an independent way of the large-scale structure. Here you see Planck collaboration. Here you can see what we have done. Now, because originally people thought that the gravitational wave background is of cosmological origin, they express it like all parameters in cosmology in terms of omega GW, which is the energy density of gravitational waves in a logarithmic interval of frequency and normalized by the critical energy density. However, on the top of the gravitational wave background of a cosmological origin, phase transitions, topological defects, inflation, whatever you want to put there. In addition on that, you have a background from an astrophysical noise, if you wish, from mergers which are far away and you cannot extract them. Okay, now the point is that when you receive some data, I'm in Fourier space, so that's why the tilde, my signal depends on frequency of my interferometer I, has two components, the strain and the noise is much bigger. So the only way that you can extract this background is if you just take the correlation of the output of two detectors under the assumption that here goes to zero. There is no correlation between the strain and the noise. And then we can calculate and we can see. We have not found background yet, but we are 4 orders of magnitude below the CMB. We are lower than 10 to the minus 9. So it makes sense why it's difficult to find. Why I'm saying that? Because I would like to just tell you what's happening when you have parity violation. Then when you have parity violation, when you take the 2-point correlator of the output of your two detectors, it's going to be written in terms of the Stokes parameters, I and V. So that's how my omega GW is going to look like, and I'm going to have a polarization degree. We have searched for polarization in the gravitational wave background data. We have not found any kind of signature. Now, amplitude damping, and that's what yesterday in the discussion panel, Stefano mentioned. Constraints on the space, if you have large extra dimensions, so what you could have gravitational waves which are leak in the extra dimensions, and then you are going to compare the luminosity distance as you get from your interferometer, and as we take it from the electromagnetic counterpart. We had just one event, the GW170817, where you have gravitational wave that we received, and 1.7 seconds after with the time lapse, we have gamma ray that they appeared. This is from the binary neutron star at 40 megaparsec away. So here is how the luminosity distance is going to change, and depends on these two parameters. This is RC, which is the scale beyond which you have leakage in the extra dimensions, and this steepness parameter N, which depends on the model of extra larger dimensions that you have. And here are the constraints. Here you see the shaded excluded regions, which depends for which values of this RC parameter you take, and you can see that there are big constraints. There's consistency with 3+1 dimensions, and it was quite interesting to say. If I was in the next when Gia was here, I was not going to put this transparency, so he just jumps because one of the models of extra dimensions here, that Valli-Capadazzi-Porati model, was ruled out. Okay, just from one event. So I found it pretty powerful to be able, with one BNS event, to put constraints in models of extra dimensions. Yes. No. Yes, we are. No, we are. They have been the gamma rays that they came from that region. Once we have an event, this is not. Once we have an event, there is an alert. Even if we're not completely sure, there is an alert that goes toward the radio telescopes and whatever telescopes exist in order to localize. We give them the position, so we know locally where the position is, and then they find this kind, which continues for quite some time afterwards, which is in agreement with what people know. I'm not in the astrophysics, but what people know about the mergers. So I think there is no doubt about that. No, I'm saying that what we found is consistency to high accuracy, if you wish, with the 4-dimension, 3+1. That's all I'm saying. There is a consistency. There is consistency with standard GR 3+1 dimension. That's all I'm saying. Huh? I'm saying that one model is ruled out because then you have to go and map which are the constraints on this RCN, RCN N, that's all. But the data themselves, they don't say they could be taught extra dimensions. They say that with a big accuracy, we are in 3+1. That's all I'm saying, not beyond that. That's all what it says. It says that we live with high accuracy in 3+1 dimensions, point. Doesn't say, don't try to put something beyond one. Well, I have this. This is an example. This is an example of a model. Okay, this is an example. Okay, you can go back and see if you have a model that its consistency gives a number of extra dimensions and a number of parameters which doesn't fit. Then I'm giving an example. What I'm trying to say here is that with just one kind of electromagnetic counterpart, from the difference that we have in the strain that we have received and the electromagnet, we were able to confirm with a high accuracy GR in 3+1 dimensions. This is the statement. Now, test of propagation. Now I'm going to say something which touches more models of quantum gravity, which we did some years back. There is a kind of process which touches many quantum gravity theories, which is the dimensional flow, change of space-time dimensionality. So what I consider here, I consider that I have my space-time, which somehow it is distorted by some quantum gravity effects, which I'm quite general what they are, which they are characterized by this measure rho, and we have this kinetic term K, and here is my source. So that's how my action is going to look like. So then I can go and I can write how the strain is going to look like. It is the convolution of a retarded Green's function and the source term, and my parameter gamma here depends on quantum gravity model you are going to consider and depends on the values of the Hausdorff dimension and the spectral dimensions here. And then you can show that you can write down at the end of the day the strain, which will depend on this function here, that depends what is your source, which has no dimension, and the important quantity is this power law distance behavior. So now you can see that you can go and write a kind of relation which is similar to the one that I saw before for the case of large extra dimension. So there is a similar relation between the luminosity distance that you read from your interferometer, the strain, and the one that you get from the electromagnetic counterpart, which is given here. So in this equation, you see that you have some scales, okay? If there is only one fundamental scale, the Planck scale, this small gamma here is the UV scale. If you have theories where there is a mesoscopic scale, is a scale at which quantum gravity effects cannot be neglected. They're important, but not the most important one. Then this is a mesoscopic scale of the order of 1. And this equation then is valid only in the infrared regime. Then I can go and I can put constraints on the parameters lambda, L star, and gamma by constraining this ratio from the data that I can have. And then I go in the literature and I see for all your preferred kind of quantum gravity, here there is telegravity as well, you can go and read in the literature which are the values of these two scales. And then I take the one BNS scale and simulated kind of data in the LISA kind of band. I can do a Bayesian analysis similar of what was done for the extra dimension. And then we can see that with electromagnetic counterparts, the only way that I can put constraint if I am in that regime, and the only quantum gravity proposals which satisfy this regime is group field theory, spin forms, or loop quantum gravity. I do not say, and don't take me wrong, that one of these theories should be the correct theory of quantum gravity. I'm saying that if I have an electromagnetic signal which comes again, with the gravitational wave signal, so with electromagnetic counterparts, only one of these three kind of proposals of quantum gravity, it will be able to be constrained. And then I have to go back to my friends who do the full quantum gravity theories and ask them, you have to look for realistic quantum states of geometry that give rise to such a signal. So that I keep saying, but nobody has done it. So we could be able to put constraint in one of these three theories. Now, what's happening actually if you do not have electromagnetic counterpart? And as a matter of fact, the majority of data we had so far did not have an electromagnetic counterpart. Can we put a constraint? And then I'm going to go back and study the propagation speed of gravitational waves. And in many of the theories of the propagation of the theories that you have beyond GR, you find that they predict that the propagation speed of gravitational waves depends on what is the energy scale. You have that in models. With the spectral dimension of space-time changes with the probe scale in Brainward models, massive gravity theories, Hordensky theories. In all these cases, you have that it will depend on the energy scale. But I have a constraint. I have the constraint which comes from LIGO. It tells me that I cannot be too far away from the speed of light. So then, in order to be able to check the validity of one of these theories which predict that depends on the frequency, I have to build somehow a way to construct a frequency, a scale dependence of the propagation of the gravitons so that I am within the speed of light for the kilohertz range that LIGO gave me. And then our question was, can, for instance, with LISA, when we'll be in the millihertz range, to put some constraints. And then what we did, okay? So what we did, we took two kind of ansatz. One is a polynomial ansatz, okay? And one is this kind which is inspired from effective field theory. In other words, I'm going to have an abrupt change in the speed, in the propagation speed of gravitons, and my models should give me constraints on GR plus constraint on these extra parameters, beta if you want, and here the F star and the C0. Okay, so these are the two models which we did. And that way you can go to do a post-Newtonian analysis, and you are going to rewrite, forget, I'm just telling you that it's complicated, it's doable. You are in a post-Newtonian kind of expansion. You write the modification of the amplitude and of the phase, and then at the end of the day, we're able to show that actually LISA will be able to put constraint in such theories where you have modification of the speed of graviton from the speed of light in the millihertz range, and will be able then to go and do a mapping with your theory and put constraints on the free parameters that you will have there. Polarization. Somebody asked the question the other day, what about polarization? And as I said, and I repeat here, polarization is difficult to do it with the interferometers that we have now, that they have the same orientation, we have very few. However, we're able to propose a kind of Bayesian approach in order for the gravitational wave background to give you some signature of extra polarization modes. And what we have, the signal versus noise have the same probability with equal kind of probability for the subscases of the signal, the same GR and non-GR. This is a method that from the second observing run and afterwards have been adopted by the collaboration, and up to now there is no kind of signature for any extra polarization beyond the two tensor modes that we have in the GR. Now, the ring down, okay? The ring down is another way that you could have some kind of deviations, and theories predict that. So what is the remnant that you will have at the end of the day? Okay, you have two primordial black holes, they are going to merge, they are going, at the end of the day, the whole thing, it gives a perturbed Kerr black hole, which by emitting gravitational waves is going finally to arrive, to relax to a Kerr stationary state. And this kind of gravitational waves which are emitted are in characteristic quasi-normal modes, which depend only on what is the mass and the speed. And this is the no-hair conjecture in GR. So then what you can do, you can go and study whether you have any kind of departure from this conjecture of the GR. We have the fundamental and the first excited kind of mode, and both they give 92% credibility with just the no hair conjecture in general relativity. So no departure from the GR. The echoes, and again, I think probably in one of the questions, and I think Stefano made a comment or said about that, you have these very exotic compact objects which are more massive than the neutron stars, but they do not have horizons. So what happens is that at some times as the gravitational wave goes inwards, then it can bound and interact with the object itself, and that is going to give a series of echoes, okay? And that again gives a characteristic waveform which has not shown any signature in the data that we have so far. So again, there is nothing coming from echoes about exotic kind of compact objects. Now, I said that I'll give some examples of model-dependent tests of gravity, and I consider, I think, 3 of them. One is the Chern-Simons gravity. So here you have this extra kind of term that is the scalar field theta, okay? And these are the constraints that they were put on the evolution of the scalar field by looking to birefringence to polarization in the gravitational wave data. And you can see this is the constraint of the solar system. This is the constraint, the green one at LIGO now, and then as we go on, the constraint will become even bigger. So there are constraints that were put to a particular model of gravity beyond GR. Another thing, it was mentioned, it was a big list that Francesca put at the formation of primordial black holes. And we have studied that for 2 cases, the cases of a cusp of a string that collapses to form a black hole. But yesterday I was not looking, I could not look for my transparency. I was tired to reproduce it. So I have another one here, which is the model that is most studied in the literature for formation of primordial black holes, is from second order from scalar perturbation. So it's through curvature perturbation. So if you know the power spectrum of the primordial curvature perturbation, then you can go and calculate what is the power spectrum of the induced gravitational waves. And then you go, you plug it here, and you find this omega GW, which is the energy density of gravitational waves that I said yesterday. Because I do not want to take a particular model of curvature perturbation, then what we did, we say, okay, let us go and parameterize them in terms of these 3 parameters, the amplitude, the position of the peak, and the width of the peak, okay? And here we're looking again in the LIGO data to put constraint in these parameters. This is the excluded region that we have from LIGO-Virgo. You see already it's much better than BBN and CMB. And as the data will become better, LIGO design or Einstein telescope, then the constraint that we will put, and therefore you can go and do some mapping in your theory of the curvature perturbation of your models. What are the constraints that you can impose? And the last thing, again, somebody asked the other day, I don't know who was, but somebody asked in the case of scalar radiation, so the case that you have an action field, for instance, and this we have done it. We did the first post-Newtonian corrections to the dynamics, radiated power, and gravitational waveform in the case that you have a binary neutron star where you have a scalar field. And so there are theories beyond GR, scalar tensor theories that tell you that. So for instance, could be an action. That's how it's going to be changed, the phase. This is the leading order correction from your action field. And this is the post-Newtonian order. And again, by just one event, the GW17 or 817, we're able to put constraint on the actions with masses in this range. And these constraints, this is the blue one, these constraints will become even better if you have more data. They will come better by square root of the number of events that we have. So all that to say that they can be put constraints in particular models by looking how they will modify the waveform and by comparing that with the data. Now, things might become much better with the pulsar timing array. Why? because what we have here is that we are in the nanohertz region, which means we have lower frequency, longer wavelengths, which means that the objects are heavier and the orbits are wider. So in that case, we expect that actually in the early spiral phase, we might have more pronounced effects of theories where we're going to have negative post-Newtonian order, and then can be dipolar deviation or extra dimensions, and we expect that more constraints could be put in theories beyond GR by pulsar timing array, and there are some more than hints that a gravitational wave background has been found from the pulsar timing array. Now, to which to be sure whether that is the case or not, we would expect to combine the results from all the collaboration, the European, the Nanograph, the American, the Australian, and so on. So last thing that I would like to say, because you mentioned that I like no-commutative geometry, and because yesterday at the discussion, it was Stefano who said a lot about how pulsars can be used to constrain models beyond GR. So I mean, any kind of modification of gravity. I will go back to some work that we did ages ago, which is with this no-commutative spectral geometry, okay, which is a mathematical model that tried to explain the standard model of particle physics. So just, I'm not going to go into detail to that because it's beyond the scope probably of what we say here. But at the end of the day, that's how the action, the cosmological part of the action would look like, plus the standard model, which I don't include. And then you have this, this is the coupling that you are going to have between your Higgs and the curvature. And this is the Weyl tensor that comes here, okay? Then I can go in that theory, is rather kind of convoluted, but at the end of the day, you can go and calculate what will be the tensor modes, okay? And now we were able to go and put constraint. Yeah, it's a scalar field. The H is a Higgs, take it to be the Higgs. Yeah, you do. No, let me finish because I want to finish what I'm saying and then you cannot. So then what I can write down, we can write down what will be the corresponding quadruple form of the rate of emission of gravitational waves, okay? I can compare that with the data which I have, and any kind of discrepancy, it should lie in the error bar. And from that, we were able to put a constraint in the extra term here, in this term here, which is related to the coupling constants at unification. So what I wanted to say that, again, with gravitational waves and from the pulsars which we had at the time, this is a paper that goes back 15 years ago, 14 years ago, we're able to put constraint in one of the three free parameters of this kind of non-commutative approach to the standard model by just constraining what will be the discrepancy that I will have in the energy that is released from the emission of gravitational waves. Now, your questions before I end. I don't know. I have not finished, but if you have a question on that thing, I stop. If not, I continue. H, I told you, is the Higgs. The Higgs of the standard. This was the model that Cons and Chamsadin had. I mean, Cons, Macaulay, Chamsadin, Cons more than anybody, I believe, there were trying to explain the standard model of particle physics. You have this geometry. Your space is given by the product, the tensor product of this four-dimensional Riemannian manifold M and this discrete space F, which you specify by the choice of an algebra, Hilbert space, and Dirac operator. And if you choose the algebra appropriately, then you get the standard model. But this is beyond the scope of what we do if you want to discuss afterwards. Yeah. No, I'm saying that I'm going to have, I write down what will be the quadruple, the standard quadruple form. You see that? And this H dot ij is the time derivative of the tensor perturbation. So now this is I'm going to calculate how the hij is here because I have different equation of motion. Okay, so I have a deviation of what GR tells me. So the deviation of the GR should lie within the discrepancy that I have from the accuracy of my data. And from there, I can constrain the parameter. So the fact that from pulsars, I was able to put a constraint in a model that, to me, it's quite powerful. It's quite powerful. I mean, that's all I want to say. So any form of gravitational wave information can constrain fundamental theories. So that I don't want to take to be in time. So the implications of gravitational wave detection, I believe, can hardly be overestimated. Now, things which I have not touched here, but I put them in the conclusions. Test of GR and extended gravity theories. I think that's what I try to focus. Test of quantum gravity proposals. I touched something upon that. Things which I have not said. Test of high energy physics beyond the standard model. We're able to put constraints 7 orders of magnitude above the ones that LHC can put. So from the constraints we put on phase transitions and topological defects. Information about dark matter and constraints, primordial black holes, actions. Information about cosmology, all the discussion that goes about H naught. Information about astrophysics, the neutron star equation of state, black hole masses, spins, so all that. I didn't try to say that Swedish because I wouldn't succeed at all. Thank you very much.
Thank you very much, Mairi. So we have actually 10 minutes for questions, I would say. You had a question already, so you can ask.
Sorry I interrupted you before, but...
Yeah, you have mentioned the non-commutativity.
Yeah.
So the question, what is the starting form of non-commutativity you have used? Is it
the model that, no, it's not a Moyal. No, it's not. It's not a non-commutative field theory. It has nothing to do with this kind of, the commutation relation. It's this model that I put there, this kind of tensor product between these two spaces. And that is and then what you do here, just because if you want to specify what you do, you go to write down the spectral action principle, which is the trace of the Dirac operator, which is normalized up to cutoff scale, which is lambda. You write that in this silly DeWitt coefficient, you expand it, and that's how you get at the end of the day the bosonic part of the action.
There was Robert and then Kelly.
Back to the slide where you had constraints on the time derivative and acceleration of the scalar field.
I think you mean, if I'm not wrong, not this one. You mean this one? It's not my work, by the way. It's a very nice paper. I discovered that paper when I was trying to do that myself and discovered that this is paper. And I could say it's a very nice paper. It's very well written, very well done by Ken Yang and Ken Yang in. So they put constraints, so they try to put constraints is in the evolution of the scalar field that I had theta that I had put, is the Chern-Simons in the weak, of course, to be applicable, to be correct, this theory to be consistent, it has to be the weak limit approximation, which means that this kind of corrections you have are small with respect to the GR.
So I guess I'm not so familiar with the units on the vertical axis.
Yeah.
So do you have any intuition for what that means if you just want
theta and double is yeah
square?
I mean, it should be.
How constraining is this in particle physics?
How, say again? How you get is the evolution of the field which you have.
Right. So it's just a question of I'm not familiar with.
Well, I don't.
Okay.
Yeah, we can discuss. I don't know. I mean, we can. Yeah, I cannot take any thing for the units, but I don't understanding the paper. I would doubt it's wrong, but we can see how it comes. You have a question. You can. No, I cannot. I cannot. I don't. Is an example. I cannot go into the no. But I don't know how this consistency, how it fits in this plot. Sorry. I gave the exclusion. Okay, I think I'll go faster if I go that way. I gave the exclusion here. From what I
For Newtonian tests and so forth, when you see 1/p corrections and so forth, that's interesting. Then they might be able to...
you see, from what I understood, it lies within the exclusion region of this plot. That's why it is excluded. I cannot see. So it lies somewhere in this gray or yellows or whatever region of this plot. The axis, it depends on this stiffness kind of parameter n, and then it depends, the first one on the space-time dimensionality, the second one on this screening kind of radius is the one above which you have this leakage to the extra dimension. But we can see it afterwards in detail where it lies in this. My understanding, it lies in the exclusion part of this region, but I cannot comment beyond that. Another question.
It's also very fashionable these days to talk about just often everybody one extra dimension. I can't remember the title it's given to.
Well, yeah, no, but generalization.
Well, I understand the sort of.
You mean the dark dimension?
Remember the buzzword.
Sorry? The dark dimension.
Yeah, the dark dimension. Thank you.
Yeah,
Dark dimension. That's what's hot on the.
Yeah, you know, at this point, I would be hard to say if there are extra dimensions, why to be just one. Because if this mechanism work only for one extra dimensions, I would be even more skeptical to adopt it. If there are extra dimensions for the consistency of the theory, as we know that exists in string theory, then they may be much more than one. If the model works only in one extra dimension, I wouldn't bet on that personally, but that's my personal politically incorrect view. Yeah, I have the paper. We can see more detail if you want where it lies there, but.
There was, I don't know what's first. Since Anne was already speaking, maybe you can finish. Yeah.
No, it's a back at the.
I cannot comment more on that model, okay? On the volatile model. So if your question has to do with that model, I cannot comment.
Go back to
Where?
polarization states.
Okay.
And this might be a sort of BS question, but presumably with your the limits on polarization states of the graviton or the gravitational radiation, one could try to
Forget, I don't know what it is. To try to do what?
One could try to constrain the scale of supersymmetry breaking. One. Because we don't see it in the data, there's no evidence of the gravitino.
So in other words, what you say, what you want to, so what you want, no, it's not here. So what you want me to, what you try to say, no, it's not here. So you want the example that I gave, not example. Keep talking, I will find it.
You had a plot.
I know, that's what I'm trying to find, but.
Well, it doesn't really matter, but
I know, that's why I said keep talking. So that's not here that you mean. It's not here that you want to be.
Well, I was just saying that maybe it's possible with the LIGO results you already have.
Yeah.
And to say that we can exclude a gravitino mass of energy below something or other. And I have no idea what that energy is. And I'm sort of looking I'm sitting next to someone who knows a damn sight more about supergravity than me.
Yeah, but you know about numbers. I just.
Maybe Robert has a point on it.
Actually, I don't understand why would the gravitino induce Planck? Well, I would expect if it was if one wrote in supergravity, then surely the gravitino would contribute to the gravitational waves. Yeah, but why would it be parallel? I'm not doing parallel violation. But this slide is parallel.
No, probably not this slide. I don't know which slide.
Okay, I think
I don't know which slide you refer to.
The usual mode of the gravity wave and the vector blah 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 ones, the extra things. And I suddenly thought, oh, I bet we could probably do something or other there on gravitino.
I don't know, but probably we can see.
maybe I think we can maybe postpone this question to the discussion, so Mary can also look at the slide later better.
I don't know which slide you refer to.
Yeah, we can maybe. There was.
Depolarization when I discussed was here. I didn't have any plot here. I just have the Bayesian thing. And that's,
Anyway,
we can find it. We can find it.
Francesca?
To go back to the beginning of your talk when you were talking about the gravitational wave background.
Right.
And the possible constraints there. Of course, the difficulty is to check against astrophysics that we don't know about.
No, because from gravitational wave, we know what we know. Can I write somewhere? What we know is that if I take this omega GW that I discussed before, okay, if I write the omega GW, it has a frequency dependence, and this frequency dependence depends what is the origin. If, for instance, is compact binary, it depends. The omega GW depends on the frequency. And if I take a kind of compact binaries, then by writing down the quadruple formula, you know that the omega GW from CBCs goes like f to the 2/3. If I have, so I know, so you see, I can test it against different laws. I know that for inflation, it's flat. And I know that for cosmic strings, then it's going to depend in which frequency you are. For the frequency of the LIGO stuff is again flat. If it's a phase transition, is a broken power law. And the position that changes has to do with the position that you have this phase transition. So I know what is the frequency dependence. So you see, there is quite some robust, and what then you do, you have in some of them a kind of a free parameter that you have to normalize against. For instance, the phase transition scale. For instance, the mass and the spin of the black holes. For instance, you know, so it's not that you don't know if you call it astrophysics or because you do know what it is behind, and you put constraints. For instance, for the case of cosmic strings, the constraints that we have are 7 orders of magnitude in the energy scale at the formation of the strings from what LHC does today. It's quite remarkable. For phase transitions, depending when the phase transition took place, we could be within the kilohertz range where it's like. So we can put constraints. So even absence of signal gives constraints.
But what about but I have in mind our bouncy models in which have a production of gravitational waves from the bounce.
Then I should know what is the frequency dependence of that. You see, because at the end of the day, once we will have our data, let's say tomorrow I have a detection, and I know that's a real detection. Okay, then it's going to have a contribution of all of that. For sure, I'm going to have a contribution from CBCs, because I know that there exist black holes and neutron stars. So for CSAS, I have an f to the 2/3. Plus, I have a contribution in different frequency ranges from all the other exotic things you want to put. What we have done at some point is to see, will we be able to make the separation? Not with 2G detectors, with 3G, probably. So if you tell me, how does it look like the frequency dependence of the gravitational waves that come from your model, then I can put constraints, because I can, if I know how it looks, you see, we did the same exercise so there is a way that I can write the omega GW I can show to you how it depends if I have phase transition, if I have defects, if I have, I don't know. If you give me that, then I can search for that in the data. Absence will put me constraints on whichever is your free parameter. But I need to know the frequency dependence.
Okay, I think maybe it's good time to, we exhausted the 1 hour. Unless you also had a question, maybe we can postpone it to the discussion. Okay, so let's thank Mairi again